So, hello, everybody. Welcome to the second part of our VHDL circuit design. Very nice. I'm very happy to see again a lot of already known people. So, again, welcome. I hope you can see my presentation. Let me just switch here to the screen, the big screen. Here we go. And now the second part. So the second part means that our first part actually was finished at the designing VHDL part. So this means the second part start actually right here with designing with VHDL. This means we just this was part number one. Now we just right here starting with the object we are going to deal with whenever we actually start designing with VHDL. Okay, this means now let's start here designing with VHDL. So the design units we are dealing with during the process of designing a circuit, the design units are entity and architecture, and so that's what we need all the time. Okay, configuration, it's used sometimes, and package is actually also used. Well, it's actually used quite often. So we'll talk about this, but let's start with definition. What is the entity and what is the architecture? Okay, the entity represents actually how does a module looks like from the outside view. This means, for example, if you would like to design module ABC, then first, okay, we should define the so-called entity. Entity means we define a port, maybe A as input, B as the input, and maybe we define output port C, and say that's the definition. So entity just shows you, well, that's how it looks like from the outside view. Architecture. Well, the architecture is, well, what's inside? What's inside? So this is the structure, the definition of the function inside. Okay, so this and that belongs together. Entity and architecture always belong together. So this means here the example. Let's assume we would like to define a module called register. So first we define an entity, register, name is the register. Now the blue one represents the keywords. Okay, so this means now we say we do have ports, so these are the connections to my module. Then we define the name of the connection. In my case, it's the in. Then we define the mode. What is it? Well, it's input, or it might be an output, or it might be a bidirectional. And then we define the type. So in this case, it's a vector. It's an 8-bit vector, dimension 7 down to 0. So now that's the first. So this means it's exactly this definition here. Okay. Now the second, it's a DOut. It's output of the same time 8-bit vector. Well, that's this one. Okay. And the last one, it's a clock. It's just a single signal, not a vector, just a single signal. By the way, it's a type definition. We'll use it also in the next webinar when I talk about the verification stuff. So, but for the time being, just assume standard logic. This is just a line. Okay, this is a digital line, a signal carrying carrying a digital signal. Okay, so that's the type. So in this case, the clock is input here, and the name is CLK. The type is inputted, and the mode is input, and the type is single bit. So it is this one. So now we declared this is how the register block looks from the outside view. Now the question, but what's inside? Then the next description, it's architecture. Now the definition, the architecture has a name. Usually we use XX or behave or whatever. So it doesn't play a really big role. It plays only a role if you would use a so-called configuration. But at this time we will not use it. So in this case, this is just a default name. We can use always the same name. But that's a reference. So that's the architecture, so the internal circuit of this entity which is called register. So that's actually the reference here. See, that's the reference here. And now the definition. It's so-called the process. We'll talk about the process a little bit later. But in this case, we can almost read it in a text, in a pure text. If there's a rising edge, then please take the data in and move it to the output. So this means, what is it? Well, this is a flip-flop. This is just a flip-flop. If there's a rising edge of the clock, here we go, then the in must be output to the out. Well, that's a flip-flop. But because the type of the data input and data output is a vector, so this means it's not a single line. No, this is 8-bit wide. So this is actually an 8-bit wide register. Very, very simple. So that's how we define the behavior of this function. So this means always a pair definition of always a pair consisting out of entity and architecture. Okay, here we go. Let me just go to the next. So this means if we just do, sorry, let me just clear it a little bit. But so just to make it a little bit more clear, entity shows you, that's how it looks like from the outside view, and architecture, that's what's inside. Okay, so this means now just two terms which are used here. It's called one time it's called structural, and one is called behavior. So this refers to the type of the architecture. What does it mean? So if you define a module, okay, so this is the definition of this is the entity. We know this already. But what is inside? It's an internal description. Could be structural. What does it mean? It could be, in this case, for complex devices, it could be definition of a hierarchy. So this means this might be it's called a structure. Okay, maybe module A and module B. So this would be a structure. Or, so this may happen, yes. This happens especially if you define a complex component, so you need a hierarchy in order to make it more readable. Okay, but sometimes at the end, okay, then might be you define an entity again, entity here, but now you just already described, well, this is something, what happens here. So this is called the behavior. So this means we always have a mix. Entity could have inside a structural description that would be a new hierarchy, but sometimes at the end of the day, well, the very last component must have, of course, a behavior description. So these are just the terms because you will see this in the documentation. So this means, again, example of a half-head. If you would like to define a half-head is a very nice, very widely used example whenever you learn VHDL. So entity half-head is, now we define port A. Here we go. It's an input. Yes, it's a single line. Okay. Carry and D. So this, you see what happened if the two ports have the same mode, okay, and the same type, then they can be defined in one line using a comma. Okay, but well, you can do. I never do this. I just spend the time and just define A and define B. Just spend the extra line. But you can do this. You can put this in the same line. And again here, now we do have two outputs, a carry and sum. Again, these both signals, they do have the same mode, its output, and the same type. So we can define it in the same line. So this means now we define a half-head, which is basically this module. A and B are input, sum and carry output, that's it. No definition, no information what is internally, because this would be the architecture part. So in this case, this is just the definition how the model looks like. Okay. Now, before we go to the architecture, let's talk a little bit more about this formal stuff for defining the ports. So whenever we define an entity, we have all the time, we have to define the ports, of course. And how to define the ports? What's the format? First, you select the name. That's your user. That's your option. You just name the port. What's the name? Okay. And the next is the mode. What does it mean? Well, is this an input, or is this output, or is this a bidirectional? It's called in-out. Okay. And the last one is the type. Okay. What is it? Is it the integer? Is the signal carrying a integer value, or is this maybe a vector? What's the dimension? 10-bit, 16-bit? Okay. Or does this port maybe carry a time information? That would be the type time. Or is this maybe something else? So this means we do have an unlimited. We do have an unlimited number of types available. Unlimited. Why? Well, I think 11. 11 of them are predefined in the standard, are predefined. Okay, but you can define an unlimited number of your own types to make it very maybe suitable for you. Okay, so again, that's actually the definition of the port. So you have to define the ports with the name, the mode, and the type. Okay, so this means let's talk about the mode. What is the mode? Input and output. Well, let's assume if this is the entity, okay, if this is the entity, ABC, whatever the name is. So now let's define, analyze the port. For example, for this signal, the port, the mode of the port would be input, because we're using this as an input. Okay. Also for this signal, its mode is an input, because we're using this somewhere here. And this is also an input, and this is also an input, because we're using this as input. For example, this port with this name, the mode would be out, because this is an output. Okay, or this one, you look to this port, it's called in-out, because bidirectional, because we use it sometimes as output, but sometimes it's input. It's called bidirectional. So this means these are the ports what we can have: in, out, in, out. So they are very obvious. But there's another port called buffer. So what is a buffer? Well, just to show you how strict VHDL is actually. If you actually define a signal here, which is output, it is an output. So actually it should be an out, because it's an output. But if you use this signal internally as an input, then the VHDL will generate an error for you, because this cannot be an input because it's an output. In order to explain this, then you have to define this port to be of mode buffer. Buffer means I'm generating this as an output, but I'm also using this as input internally. Just to make this clear, you have to find this buffer. I'm not using the buffer because this is something artificial. This is something, it's not really real, because it's in the real world, it's an output. So I'm not using the buffer. There are very, very nice workarounds to avoid the buffer. We will see it a little bit later. So usually what we do, we just use these three modes: in, out, and in-out. This is what we actually have to do. So this means the formal way now to define the architecture would be, in this case, so we define architecture with a name. That's actually just a name. Again, could be whatever you like, but that's a reference. Now that's a reference to the entity, because this architecture belongs to the entity. And then we do have a specific declaration area. Here we go. And begin is just to distinguish between the declaration area here, declaration region, and actually your statements, your activity statements. So it's a begin. And now you define here what's inside architecture. So this is a formal way. Very, very often we have to use the declarative statements right here between is and begin. For example, if we need internally to use maybe some signals to describe something, some signals, then you have to define first the signals right here. And again, because the internal signals is just a connection from A to B, so this is not a there's no directed somewhere, there's no mode. So but for the definition, you need a keyword signal. Well, and then say a signal Q1, maybe Q2, Q3, and it's a type. So you need always, the type is always needed. Signal, this means, well, I have a connection internally, and before you can use the connection, for example, the connection connects the unit A to unit B, then you have to, and this, let's call it maybe the signal Q1. Before you can use this, you have to declare the signal that this is available. Okay, so in this case, if, to make it complete now, if we just define the half add, then first we define the entity, and then internally in the architecture, very simple one, we just define internally sum is A XOR B and carries A and B. And please note the declaration area right here, it's empty. There's nothing in there. Why? Why we don't need why do we need don't need any definition? Well, now the rule. All the ports, so in this case A and B and carry and sum, all the ports which are used for the entity declaration are already complete defined and can be used immediately inside for doing the description. So this means there's no need for the ports signals to be declared here. We can use this immediately. Therefore, well, these are the only signals we will use A, B, and sum and carry. So we don't have any declaration area. Well, this is actually rare. Usually we do have, of course, because it's a very simple architecture, but usually we do have, of course, some declaration stuff here. So this is just a very simple example. Now, let me just here. So this means if I just look to another example, so this means I would like maybe to define a simple decoder. So I define first an entity, very simple one. So A and B and C and D are the inputs. And I would like actually, and tip select is output. Here we go. And you see that's a description, very simple, a Boolean description. Chip select is A and B or not C, and then again X or D. So this means I'm using an AND gate, an inversion, OR gate, and exclusive OR. Okay, and please note, use parentheses. Use parentheses in order to make really clear what is your intention. So that means now everything is clear. Now, when we run the synthesis, then the synthesis tool will actually analyze this and will give me immediately, will translate immediately this description, will give me an let's say an will give me an schematic of what is the translation actually of text to schematic. This is called elaboration. So elaboration is not really the synthesis. Elaboration is just the translation of your description using the generic elements like gates. So in this case, that would be the translation. You see, that's using generic information, and then you understand. Yeah, that's okay. That's my intention. That's exactly what I need. So this step could be used very nice for to check your results, if you like. But then, if you continue and say, well, do for me the implementation now, then you will get this this netlist which will be implemented. You will get an input level shifter connected to the pads A, B, C, D, and so on. So these are input level shifter. Depending on the type of input, could be CMOS or could be TTL or could be whatever you like. Then you will see here actually the lookup table, and you from the first part, maybe you remember that the lookup table is exactly the location where the combinatorial logic is implemented, using a lookup table. So this means it's actually a lookup table implementing exactly this location. You see the contents of this lookup table is nothing else as this truth table. You see, these are the 4 inputs representing A, B, C, D, and this is the output. O, this is the output chip select. And you see, that's nothing else. This is the truth table. If you take your time and just analyze this statement here, and then draw your truth table for this, you will get exactly this. So this is actually the truth table for this function. Of course, it's just a snippet because you have to slide and to see the complete window. So because in this case it's A, B, C, D. So we do have here 4 inputs. This means you do have here 16, 2 to the power 4. We do have 16 entries here, which are built into lookup table. And then again, that would be the output buffer. And this is again the pad called chip select, and this would be mine FPGA. So this is exactly what happened during synthesis. Okay. Or, for example, you do maybe an adder. So in this case, you define A, B, C, D, 4 input vectors of 8-bit wide. Okay. So now, and then what you do now here is you just it looks a little bit, let's say, a little bit complicated, but it's not. What you basically see here is sum is nothing else as A plus B plus C plus D. That's actually what we see here. And actually, that's actually what we see here. You know, this is A plus B, this is plus C, and this is plus D. Okay. So now something to note first. Just you need to understand then whenever you add 2 values, A and B, and the values are 8-bit, for example, okay? Don't think and don't expect. The human will expect, but not VHDL. Don't expect the result will be 9-bit. But that would be the correct 9-bit, but don't expect this because VHDL is not doing this. So this means if you have to explicitly define that the output will have a bit growth of 1. If you add 2 8-bit values, you will get a 9, but you have to say this. And this is, for example, in order to do this, what you have to do is something like this. You take A, let's say, can keep this with 8, but then you will take B, extend, maybe with a 0 extend or sign extend, this B with 1 0, extend this gives 9-bit, and now do the add, and now we get a 9-bit. So in this function is called the resize. So what I'm doing here, I just take this signal, do the resize, because now I have to, because I do have here this structure. This means this is 8 and this is 8. Because this is 8, this must be 9. So this means then I have to extend this up to 9, because 9 plus 9 gives 10. And because this is 10, I have to extend this of 10 in order to have 10 to 10 to be 11. Okay, so this means if for example, 8, 9, 9, 9 is 10, or something like this. Okay, and then you can actually define this one here. Okay, so this is the description how we actually do this. Okay, this means is this correct? Yes, yeah, that's the number. It's 11 and 9 down to 0 would be 10 bits. Okay, so that's actually the definition of this adder here. Or but again, important stuff to understand here. Please note the following. What I'm doing here, let me again write it here. Just if I just don't use the resize to make it simple, then we get sum is A plus B plus C plus D. If you don't use any parentheses, you will really get the implementation from left to the right. It's A plus B plus C plus D. Then it will end up with this structure, like a chain. Okay, but maybe you don't like to have the chain. Maybe you would like to have a tree. Maybe A plus B in parallel C plus D, and then do the sum. Okay, so in this case, we would have to write it something like this. It's A plus B, but now use parentheses, plus, again use parentheses, C plus D. So in this case, the VHDL compiler will do in parallel A plus B and C plus D, and then implement this one. So this means sometimes this structure is of advantage, but sometimes this structure could be of advantage. Depends on the timing relationship of all of your signals. So, but you can influence this if you like. Okay. Then again, if you would like to implement a counter, then you write something like this. You define a clock and you define output Q. Please note Q is an output. Q is an output. So this means, but what is the definition of a counter? Here we go. If there's a rising edge, then U value is nothing else as the previous value plus 1. So this means actually if I write this, I would say Q is Q plus 1. But this is wrong because Q is defined as output. You see here, output, but this is okay, it's output, but this would be used as an input, so this is not correct because on the right side of the equation, so this would be an input. You will get immediately an error. So that again, this was what I talked. Actually, we would need a buffer, but I don't like to use the buffer. So now the very simple workaround. Whenever you do this, you need maybe an internal signal which is used again for something. Okay, then what you do first, you define an internal signal. You see a declaration area, maybe call it QI. No, you describe everything using QI, everything. But at the end of the day, you say Q is QI. So this means you work internally, but then at the end of the day, you actually do this. So in this case, you overcome the buffer. You just use in and out. So this means that this case will get it would look like this. Okay. So this means this would be QI, and then finally you just define here the buffer output, and this is nothing else as Q is QI. So this is Q is always an output as defined here because it's an output, and QI is the internal signal which is used always. That's what I do all the time because I don't like to deal with buffer because buffer is not real. It's an artificial construct. Okay, because it's an output. That's it. Okay, so let's use an output. Okay, here we go. This means signal declaration, like here, we need sometimes actually to define internal signals. That's called a signal declaration. Again, just as a rule, if you use in the entity, if you use the ports, then you can use this signal immediately inside your description, immediately. Okay, but again, this is actually it happened. It's rare because usually you do need some internal signals, but this is actually the rule. All signals which are used in the entity might be used immediately in your description. Okay, but like here, that's again the definition. We know already the example, so we use the signal here, and we can use it immediately. Okay. What? And now the information now. how can I use this entity in architecture? Well, this is actually a component what I described. Sorry. This is actually a component, some inputs, and in this case, some outputs. So this is a component, it's called half-head. So what I can do, once I describe this using ancient architecture, now I can use in a higher level, I can use this component maybe twice and connect it somehow here, maybe, whatever I do, okay? So this means once I define a component, I use this component in the next hierarchy and place this as a function. So this means once you define your entity architecture, you can immediately define this to be a component. So you see, the definition of to be a component is the same as the definition of entity. And then in the architecture of this module, we can use this component in order to describe this function. Okay. And well, just to make because this is very important for us to understand this, let me do a very simple example doing something like this. Okay, just to repeat what I explained to you here. So this means what I would like to do is I would like to make let's say, yeah, a full add. So what is a full add? Well, full add is it's a very simple function which is used a lot for some examples. And full add is nothing else as two half adds. So this means first we do a half add. Okay, what is a half add? Well, the half add is able to add, here we go, 2 bits. So this is A, this is B. So this means if I use A and B and XOR, so this is the sum of the 2 bits, whatever it is. And if I use A and B as an AND, so this is the carry. And so this means a half add is able to add 2 signals A and B and produce a sum and a carry. Well, that's nice, but unfortunately, I cannot use really just a half add to add more bits, because in order to add more bits, I need maybe a carry input. If I do, not just single bit A and single bit B, I need maybe a 4-bit vector A and a 4-bit vector B. I need a carry in from the previous stage. So therefore, I need the so-called full add. So what is a full add? And the full add is this. We just use half add. Here we go. Which has the pins A and B. Here we go. Okay, and we connect this A here and B here, and then this would be the sum output, and this would be the carry output from the half add. Now, we just take a second half add, because in order to have a full add, we need 2 half adds. So in this case, it looks like this. Then we just connect the sum to the A, so this is the half add 1, the same, let's call it half add 2. And again, the sum is already the output. Here we go, that would be already the sum of the full add. And the B is, so this would be the A and this would be B, this would be the carry in, that would be connected to this one. And then this carry and this carry both all together. This is the carry of the full add. So this means that would be the full add. That's the theory, okay? So now I have a very nice element called full add, which can be now, combined together to actually to define, an n-bit adder. For example, now I would be able to actually define this adder if I would like to do this, okay? So for example, maybe first a symbol, let's say a 2-bit and 2-bit here, okay? A and B vector, the output would be 3 bits. How it would look like? Well, in this case, I will take a full add here. And a full add here. I need 2 full adds. So now I just connect. So in this case, I connect A0 and B0. Okay, so this is always one line. There's no carry in the initial, so this means the carry in is 0. And this again gives me the sum 0. Then the carry out of this full add carry out is connected to the carry in of this level, and this is connected A1 and B1, gives me sum 1. And finally, let me delete this one. Oh, here we go. And finally, the output carry out of this is nothing else as sum 2. You see, 2 bits plus 2 bit gives me a 3-bit result. Here we go. 2 bit here gives me a 3-bit result here. You see, that's actually what happened in VHDL. We work all the time. We do work with hierarchy. First, we define a simple element, then the next higher element, next hierarchy, and then again next higher element in next hierarchy. That's what we do all the time. And this is actually described here. But now, let me do an example just to show to you how this really works. So I just I just call Vivado with the empty project. And first I define, let's call the project, it's test. Okay, here we go. But now let's first define a half head. First this one, then I will use half head use in this hierarchy, and then finally use this in this hierarchy. Okay, so first I define a half head. Here we go. So I say, give me a source. I would like to have a create a sign source. Okay, here we go. And I create a file and I call the file half add. Okay, half add. And finish in the pins which I'm going to use here is I do have the pin A, I do have the pin B, and I do have the pin sum is output of the half add, and carry, that's called the C out, is also the output of this half add. And here we go. And now I got already the entity as described. You see here, if I just open this for me, I can remove this one, I don't need it. So you see here, that's entity definition, AB, that's what we define. And we know that for the half add, the description is simple. This description is sum is A, X, or B, and carry is C out is A and B. So let's no definition at all here. Okay, let's do this. Sum is A, X, or B. Here we go. And C out is of course A and B. Now I just do a save. No error at all. Now let's do the elaboration. Just ask the synthesis. How does my description looks like? Okay, and what I expect. Well, I do expect actually exactly this structure because that's what I did. Okay, so now here we go. Just now I need to open the tool. It takes a little bit, and here we go. Few seconds. And here we go. You see, A and B XOR gives me the sum, and A and B AND gives me the carry. That's exactly what we expect. Now we are here. Now let's actually use this half head to build a full head. Okay, here we go. Now I go back and say, good, let me close the elaborate this sign. Okay, good. Now a new source, and I say now I would like to have a full head. Full head. So this case, full head. Okay, and finish. And now he asks me, okay, what's the entity definition? Well, again, I have the A and I have the B and I have the carry in, and I do have again maybe the sum is output. Oops, sum is the output out, and the C out is here the out, for example, the out. Okay, and now I have here the new definition now, full head. So if I open the full head, you see that's how it looks like. Again, the entity. Oops. So again, the entity definition here. So this means now I do need to describe this full head, but now be careful. What happens now? What is the rule? Whenever we would like to describe this architecture, we have to first declare everything which is inside the architecture but not visible from the outside world. Let's assume this surrounding, it's not transparent. You don't see what's inside, but what you see A, B, carry in, and sum and carry. So this means you can use this signals immediately for you during your description. But what we don't see is, for example, this signal. What we don't see is, for example, this signal. What we don't see is this signal. And what we also don't see is this component. And this component is the same, but we don't see it. That's the key point. Now, before I actually can describe this architecture, I need to do some preparation. First, I have to declare, hey, there's a component called half, and I will go use it. Then I have to define, I will say, hey, there will be a signal, let's call it S1, I will use it. There will be a signal, let's call it S2, I will use it. There will be a signal, let's call it S3, I will use it. First, I have to define a lot of stuff, and then actually I can do it, okay? Now let's do it. First, let's define the half head. So how to define the half head? Well, it's simple. You just go to half head and just do a copy. Just do a copy here. If you do copy, and go to the full head. And then in the declaration section, again, remember, between is and begin, this is the declaration section. Just do a paste. And then replace the keyword entity through component. Say, that's a component now. Now, that's called the declaration. This means I will use sometime later. I will use a half head here. I already declare it. Okay, now I have to declare the signals S1, S2, S3. All of them are of the same type. This means I can use one statement. Now, declaration signal S1, S2, S3 are of type standard logic. Standard type. Now I declared also the signals. Now I did all the preparation work, and now I just do the instantiation and connection. So this means what I have to do now is, now I have to take this half head, let's call it maybe U1, must be a unique name. I will call this maybe U2. So this is a unique reference designator. So, and then just place it. How to do this? And you will see this in your presentation, in your PDF. This actually this one. You just take this and do a copy. Just do a copy here. Copy. And say here, U1, let's call it U1, is nothing else, and that you are paste. Take the half head. And now connect the ports. It's called port map. And now first the name of the port. First, name of the port. So what is the name of the port? These are the name of the ports. Here, these are the name of the ports, okay? First, and then connect this to the signals. And this A is connected, the port A of the first one is connected to signal, well, to what signal? Well, in this case, you see, the name port A of the first is connected to a signal called A, okay? Port A is connected to A, and comma. What is port B? Well, port B is connected to B, okay? Port B is connected to B. Here we go. Now, port SUM. Well, port SUM is connected to signal S1. Here we go. Okay. SUM is connected to signal S1. Good. And C out is connected to signal S2. Okay. Here we go. S2. And that's it. Now we finished actually the instantiation of the first half hat. So this means this is completely done. Now let's do the second one. Let's go the second U2. So I can actually do a copy because it's very, very simple. It's similar. I just do a copy, okay, and then replace it. So for the U2, okay, U2 now. So the input port A of the second is, the input port A of the second is connected to S1, okay, S1. The B is connected to carry in. Here we go. And the SUM is connected to SUM. Okay. And the carry out is connected to S3. Okay. Almost done, because now I do have now to describe the carry here. It's an OR gate between S2 and S3. It's an OR gate. So this means output is here carry out of the full head, and just a description. And the carry out is nothing else as S2 or S3. Here we go. You see what will happen now? Because I have a file called full head, and this file full head, in the architecture of the full head, I'm using the component half head. Now the synthesizer will understand this hierarchy relationship. And now look to my project definition here. If I just do a save, then the complete stuff will be reviewed. And you see the new, let's define this as top level now, and you see what happened. Now the tool tells me, well, you do have a component full head, which consists internally of two subcomponents. And now I can actually do elaboration here. And if I open this, then you see what you get. That you will get actually this picture, because that's what I described. Now I'm expecting this one. Okay, here we go. And then you see that's exactly what I told you. That's a full head consisting out of U1. You can even look to the U1. This is the first full head, and this is the half head, and this is the second. So this means, you see, that's exactly the definition of the full head. Okay, now we are here. Now we are here. Now I would like to go even the next step, and to use again this two full heads to define actually an adder which adds 2 bits. 2 bits, 2 bits, and gives me 3 bits. Okay, so now let's do the next step. Again, let's I just close the elaboration here so I can oops. Now I just say I would like to have a new. Now maybe let's call it adder 2-bit or something like this. Let's call it adder 2-bit. Here we go. Now I say finish, and now I say give me A, or let's say yeah, let's call it input A just to show you. You can use also different name. It's a bus, 2-bit. You see? Let's call it. Then we have input B. It's a bus, also 2-bit. And now we do have sum. Let's say output sum. Output sum is actually also this is an output, and it's actually 3 bits. Okay. Now say that's it. Now I got the new definition. You see, if I open this again, I see now the entity is a little bit different because now we're using actor because I define the vectors. Here we go. But now I'm using again, and that's the same procedure. I just take again my full add. Here we go. Just do a copy here, copy. Just go again and say this is the component. I can type it in, then just do the paste. Here we go. Add component. Now I define the full add component to be used. Component. And now I just do this description. Again, maybe I call this again U0 maybe, and again this U1. Or no, let's call it a full add 0 and an instance full add 1. So just spend the time, use meaningful names. We will see this later in the simulation, for example. So use and then connect this. Okay, now I say first I just again do instantiation of U0. So this means full add 0 is, now I just do the instantiation. You see, just take the full add 0 and again port map again. So what is the A input of the full add? Well, the A input, this is 0. The A input is input A0 and B is input B0 and carry in is 0. But carry out is, well, I need to define, of course, this signal. Let's call this carry. You need this signal because this is internally, I have to define it. Okay, now I define a signal carry because I will need it. Carry to be of type standard logic. Now, you see, now just connection. A is connected to input A of 0. Here we go. B, copy. B is connected to input B. Oops, 0. Input B of 0. Okay. And this is, of course, a comma here. So now, carry in. Well, carry in is connected 0 because there's no carry on the input. Okay. It's connected to 0. Okay, let's just connect it. Let's connect this to 0. It's 0. A little bit nicer here. And the sum, well, the sum is connected to sum 0. And the carry out is connected to a signal called carry. That's what I defined. Okay, the sum is connected to sum 0. I think I called it output. Output 0. And the carry key and the cout was connected to carry. You see? Oh, this was a typo. No. So now I just just type a signal. Sorry. So now I define the this one. Now I just place this one because I have to have 2. And this is very similar to this, so I can do a copy. You see, especially in VHDL, there's a lot of actual copy. So I can do it maybe here because then it will match my block diagram. Again, full add 1 is the same full add, but now this is connected to input 1. B is connected to input 1. carry in of this guy is connected to the signal carry, and some is some one, and of course this one is carry out of this is of course now connected to carry output of 2. You see now again, if I run a saves here, then you see now again, just let's say the top. You see now the full hierarchy. The complete adder consists of 2 full add, but the full adder consists of half add. So that's called hierarchy. Now let's do again the elaboration here. And you see now we will get exactly, that's what you do all the time. This is the designing of VHDL. Okay. Now, if you do the elaboration, then you will see exactly what we expect. I do have 2 full adds. So these are index zeros connected here, connected here, and these are the sum. Here we go, and this the full add again connected with 2. Let's just open this one maybe. You see this first full add is completely expanded. The second, no, I can expand all of them. You see, and then finally, okay, and here we go. That would be the complete definition. Very, very simple. So this means what I did here is I used actually the so-called instantiation of predefined entity architecture descriptions. For example, first I define half add, and then I use the half add right here as a component. Then I define the full add, and then in the new hierarchy, I use the full add. And so I just, just build it up. And that's exactly what is described here. We define first something, we define it, and then we use this as a component, and we just use this in a next hierarchy. And again, this is the instantiation. You take the component, say, have port map. You have the extended port map, and now first you name the port of the component. This is the port, and then the signal name to which signal the component is connected. Okay, so and that's you can do it this way. Just to explicit what I did. You name the port and port name, signal name, port name, signal name, or you can omit using the port names and signal. You can just use the signal names. But in this case, the position is important. 1, 2, 3, 4. You just name just the signal names, but you take the position 1, 2, 3, 4. So this means it's this position. In the component declaration, this is 1. Oh, sorry. The component declaration, this is 1, 2, 3, 4. So I don't like this, so I'm using this, but it's your choice. You see? Again, this is exactly the what I did. I defined the half add, and then I defined the full add. Again, another example. You see, for example, I do have an entity called top. In an entity called top, I do have maybe 2 inputs, I1, I2, and outputs O1, O2. This means this is the entity top, and I do have actually I1 and I2. So those are the inputs. Here we go. And O1 and O2 are the outputs. Okay. Now, my intention is actually to build this circuit called top out of 2 components. One component is called sub A, and another component called sub B, like full add. So it's called sub A, sub B. So now, what is the description of this architecture? Here we go. So that's the architecture of the top. First, we define the component sub A. That's exactly the definition of this. Nothing happened, just a declaration. Now we declare the component sub B. This is this. Now, because bus A as a signal is not visible from the outside world, I have to define the signal first here. And because sig1 is not visible, because the entity is not transparent. I have to define sig1. So you see, that's all the declarations of nothing happened. Now I start, and now I do the instantiation. I call this U0. Take the sub A and now connect it. Again, now I'm using here by position as an example. So this is 1, 2, 3, 4. This means the first port, this is A1, is connected to I1. Yes, A1 is connected to I1. Second port, second port is A2, connected to I2. Yes, A2 is connected to I2. Yes. Third port is the third port is 3. A3. Okay, A3 is connected to sig1. Yes, A3 is connected to sig1. Last port is called A4, is connected to bus 1. Yes. So this means this is okay. Now we just repeat the same with sub B, and then you see that's exactly how you build the hierarchy. Spend here again a little bit more time here to explain to you very well, it's detailed how this happened. This means in the next, actually, just because I don't like to again to delay this webinar, but again in the next webinar, which this webinar continues, I talk about the actually the behavior and all the stuff, and we will actually also call about operators and also the type concept, because that's what we need for our for our simulation. So again, please, if you look to your material, so because you will find in the menu, you will find our overview of our webinar series, the calendar, and also if you have any detailed or specific question, just send us an email and we will answer this. Thank you very much for all of your attention, and that's actually the end of this part, and we will continue with the next part. And in the next part, we will talk about again operators and also behavior modeling, simulation, and all this stuff. So I wish you a good day, and goodbye for now, and hopefully we will meet again maybe for the next webinar. So goodbye.